All right, ladies and gentlemen, in this video I am going to be going through the many different types of molecular geometries that covalent bonds can take on based on how many electron domains, how many bonds, and how many lone pairs they have. So as a refresher, we talked about this in class. There are 5 categories of shapes. That's how I refer to the electron domain geometries. There are 5 different types of shapes. If you have 2 electron domains, then we call that a linear shape. If we have 3 electron domains, that's trigonal planar. Again, remember these shapes come from how far apart we can put these electron domains because they're going to repel one another, so they want to be as far away from one another in 3-dimensional space as they can be. If we have 4 electron domains, they take on a tetrahedral shape. 5 is called trigonal bipyramidal, and 6 is called octahedral. And recall, one category of these shapes, meaning trigonal if we take the trigonal planar category, that is a category. And so there are actually going to be a couple different molecular geometries, a couple different specific types of shapes that we have in that particular category based on how many bonds, how many lone pairs we have. So you should have your molecular shapes note chart, and you're going to be filling that in as I go through this, this lecture. So first up is the linear shape, and I'm just going to put everything up here. 2 electron domains. Remember, an electron domain is both a bond and a lone pair. And single, double, triple bonds, they all count as one electron domain. Because electron domain is like an area of space where you can find electrons. So double bond is just going to be one single area of space. So for the picture, you would want to draw this. So this is your picture. That's what you're putting in the big box in the middle. Number of electron domains, if you look on the left-hand column underneath where it says linear, well, this has 2 electron domains, so that's what you're filling in there. Now, the bond angle for the linear shape, 180 degrees. Because, you know, you have 2 electron domains, the farthest apart they can be from one another is 180 degrees. The general formula, meaning what types of compounds have the pattern that will be this linear shape, well, this is our general formula right here, meaning AX2. For example, CO2 is linear. It fits this pattern. This is what it looks like. And on that very last column on your note packet, number of bonding sites versus number of lone pairs off of the central atom. Well, A is our central atom right here. There are no lone pairs represented in this structure. Right? We would need to see those individual dots coming off of the A, and we don't see that. So this linear molecular geometry that is also a linear electron domain geometry has 2 bonds and 0 lone pairs. Okay, so linear, 2 bonds, 0 lone pairs, 180-degree bond angle, looks like that XAX, straight line, hence linear. And next up is trigonal planar. So trigonal planar is the category of shape. Okay, so trigonal planar up here on the top, this is my category. And then the trigonal planar that's right here, this is the molecular geometry. So you'll notice that we actually have within the trigonal planar category, we have a specific shape that is called trigonal planar. So like the very first shape that we have in the trigonal planar category is actually trigonal planar. It's the name of the category as well. So in the trigonal planar molecular geometry, the specific type, we have a central atom that is bonded to 3 atoms. So there are no lone pairs coming off of this central atom. It's simply an A that's bonded to 3 X's. So again, this is your picture. That's what you want to draw in the big box in the middle. Number of electron domains. Again, electron domains, bonds plus lone pairs. There are 3 electron domains for trigonal planar, for this trigonal planar molecular geometry. 3 of them. Bond angle. How far apart in 3-dimensional space can we put these 3 bonds? We can put them 120 degrees apart from one another. That's as far apart as they're going to get. General formula, AX3. are boron compounds that don't obey the octet rule. They will very, very typically have this trigonal planar shape. Additionally, if we have things that have, for example, two single bonds and one double bond, and that's all they have, no lone pairs, then they'll typically take on this trigonal planar shape as well. Number of bonding sites, number of lone pairs. Well, if you look around A in the middle, it has 1, 2, 3 bonds. But you look around A in the middle, you also don't see any lone pairs. So there are 0 lone pairs, right? 3 bonds and 0 lone pairs. But for the first time, because we didn't see this with the 2 electron domain category, we also have another molecular geometry that's within the trigonal planar category of shapes that is not identical to the name of the category, and that is the bent shape, the bent molecular geometry. In the bent molecular geometry, now, instead of simply having the 3 bonds like we did in the trigonal planar molecular geometry, we still have 3 electron domains, but they're not all bonds anymore. Now we have 2 bonds and 1 lone pair. This is still in the trigonal planar category because it has 3 electron domains, right? It absolutely has 3 electron domains. So it's still within that category of shape. However, not all of the electron domains are bonds. So we call it a different molecular geometry. This is called bent. So number of electron domains under this bent, you want to put 3, because it does have 3 electron domains. But then you want to draw this picture, and this right here, this is a lone pair. That lone pair, because it's electrons, is absolutely still going to engage in some repulsion and push those bonds away from one another. The bond angle is less than 120 degrees. And when we say less, we don't mean like 105 degrees or 80 degrees. We mean like 119 degrees, 118 degrees. And it will vary. I'm not giving you a specific number because it will vary depending on what the compound is. What happens is that the lone pair causes additional repulsion. Because the lone pair is held closer to the central atom than the electrons that are in the bond are. So that lone pair is kind of pulled a little bit closer to that A, which means that it's going to repel the bonds between A and X a little bit more than they normally would be. So that's why we're saying our bond angle is less than 120 degrees. That lone pair causes some additional repulsion. General formula, AX2E1. The E right here means 1 lone pair. Right, that's what that E is indicating, E for electron, or electron pair. And number of bonding sites versus number of lone pairs. Well, we have 2 bonds, right? 1, 2 bonds, so 2 bonding sites, and we have 1 lone pair. So all in all, we have 3 electron domains, but we give it a different name from trigonal planar, from the one that's right at the top of the page, because not all of the electron domains are bonds. So when we get into the specifics of how many bonds versus how many lone pairs, we have very specific names for these molecular geometries. Again, they're all falling under a general category of shape based on how many bonds and how many lone pairs. So the next category, so now we're moving on. Now we have 4 electron domains, right? 4 electron domains right here. And this is called the tetrahedral category. Anytime you have 4 electron domains, you're going to have you're falling under the tetrahedral electron domain geometry. The very first type of shape within the tetrahedral category is also called tetrahedral, because all of the electron domains are bonds. Notice that that's kind of how we're starting. We started with trigonal planar with all 3 of those electron domains being bonds. Now we're starting with tetrahedral with all 4 of those electron domains being bonds. That's definitely the pattern. These things follow a pattern. So we want to draw this picture, right? This picture right here. Now, the way that we have of drawing it, this little wedge thing, that indicates that the bond, again, this is trying to show 3-dimensional space in a 2-dimensional manner. So this indicates that the bond is coming towards you. Like, it's coming out at you out of the computer. And then the dash means that the bond is going into the page. So it's going away from you. So this is showing that, this thing exists in three-dimensional space, and that in three-dimensional space, the farthest apart the four things can get is actually not 90 degrees. That's as far apart as four things can get in two-dimensional space. Molecules exist in three dimensions. When we have three dimensions, we get this 109.5 degree bond angle. So that's our bond angle. General formula, AX4, CH4 is a great example. Anything, carbon with 4 bonds is going to have this tetrahedral molecular geometry because it has 4 bonds and 0 lone pairs, right? So 4 bonds, right? We see 1, 2, 3, 4 bonds. But there are no lone pairs coming off of A. There's none that are drawn here, so 0 lone pairs. So a total of 4 electron domains, right? And they're all bonds and none of them are lone pairs. But then, we can still have the tetrahedral category. Remember, this is always up here. This is our category of shape. 4 electron domains, but those 4 electron domains, they don't all have to be bonds. So we then have the specific molecular geometry of trigonal pyramidal. And that's how it's pronounced, by the way. Trigonal pyramidal. You want to lay on that second syllable, bring all your Western New York nasal accent into play. Trigonal pyramidal. It's not pyramidal. Sound intelligent. Pronounce words correctly. The trigonal pyramidal shape, we still have 4 electron domains, right? So we're filling that in at the front. It's still 4 electron domains, but now we have a picture that looks like this. Instead of all 4 of those electron domains being bonds, now we have 3 of them being bonds and 1 of them being a lone pair. The bond angle is less than 109.5 degrees. Again, that is due to the additional repulsion caused by the lone pair that is coming off of the central atom. General formula AX3E1. Remember, E1 indicates that we have 1 lone pair. So in that very last category, number of bonding sites versus number of lone pairs, we have 3 bonding sites. 1, 2, 3 bonding sites. So this is the three bonds. But then also coming off of the central atom, we have 1 lone pair. So that's a total of 4 electron domains, but they're not all bonds. 3 of them are bonds, 1 of them is a lone pair. And it's called trigonal pyramidal because, if you think about this, the lone pair doesn't really show up necessarily. We don't see it. It will occupy space, but because electrons are so small in terms of the rest of the atoms, we're not going to visualize it as well. So it does kind of look like a little pyramid, hence the pyramidal aspect of the name. We also have bent. Again, this is within the tetrahedral category of shapes. This still has 4 electron domains. In the bent shape, bent molecular geometry, our central atom is bonded to 2 atoms and 2 lone pairs. So the bond angle, so we still have 4 electron domains. Remember, this is actually a different bent than the bent that is in the trigonal planar. Apparently, we got really lazy with coming up with names, and so we recycled the same names. We said, hey, they both look bent, but they have different electron domain geometries. One has 3, one has 4. So the bent, this particular bent has 4 electron domains, but again, drawing in this shape, we have 1, 2 bonds, and 1, 2 lone pairs. So again, this is our general formula right here, AX2E2, indicating that we've got 2 other atoms bonded to the central atom, but we also have 2 lone pairs. And the bond angle, it's less than 109.5 degrees, but we put the sort of the double less than 109.5 degrees to indicate that we're getting even more repulsion coming off of those 2 lone pairs, right? You have 1 lone pair, you have some repulsion, you have 2 lone pairs, you have even more repulsion. All right. Next up is the trigonal bipyramidal category of shape. Now remember, this is when we're moving into our what we call the expanded valence shell. So now we are going to be talking about equatorial and axial positions. We have 5 electron domains. So in the category of shape, remember the title, the thing at the top, this is saying this is like the category, meaning 5 electron domains, that's the category, and then the name right here, this is the molecular geometry, the specific type of shape within the category of shapes. Putting the picture up. This is what the trigonal bipyramidal shape molecular geometry looks like. We have five electron domains. The first type of shape within having 5 electron domains is to have all 5 of those electron domains be bonds. Ca, that stands for central atom. So that A that's in the middle, it's bonded to 5 atoms. So we have 5 bonds. And there are 0 lone pairs. We see no lone pairs coming off of that A, so 0 lone pairs. General formula, right, AX5. Now the bond angle here, notice there are actually 2 of them, 90 degrees and 120 degrees. We see the 90-degree bond angle here. This is between, so this is our axial, right, axial top and bottom. I tend to think of it like a ballerina, right? Axial ballerina and her tutu. That's what, in my opinion, the trigonal bipyramidal category of shape kind of looks like. So we have the head and the foot of the ballerina, and then the equatorial is the tutu in the middle. So between the head and the tutu, we have a 90-degree bond angle. Right, that's that one right there, 90 degrees. And then within the tutu, in the circle in the middle, we have a 120-degree bond angle. So this one right here, this is axial to equatorial. The 120-degree bond angle is equatorial to equatorial. And we'll look at that more in depth in class. This is something that's very hard to see in a two-dimensional PowerPoint presentation. So you'll see that in class, what I mean by the separation between the 2 types. Then, then we got really a little funky with our names of our shapes. Within the trigonal bipyramidal category of shapes, meaning we still have 5 electron domains, the next specific molecular geometry is actually called seesaw. So we go from trigonal bipyramidal, which sounds very, very technical, to seesaw! Yay! Because that's apparently the best that we could come up with. Personally, I actually really like the name seesaw because it is very descriptive, and when we look at this in class, I'll sort of show you where the seesaw is coming from if you can't see where it's coming from in this picture. So we still have 5 electron domains, right? So this is still within the trigonal bipyramidal category of shape, but we have 4 bonds and 1 lone pair. That's where the 5 electron domains are coming from. That's that AX4E1. And right, and this right here is our molecular, this is what the picture will look like. So this is our lone pair. And notice that we put the lone pair in the equatorial position, because that way it will be farther apart from other things. It will have a 120-degree bond angle between the other bonds that are in the equatorial position, so we can actually get the lone pair a little bit further away from other things by putting in the equatorial position. If we put it in the axial position, it would only be 90 degrees away from other electrons, versus if we put it in equatorial, it'll be 90 degrees away from some electrons, but 120 degrees away from others. So we can get it a little bit further away by specifically putting it in that location. So our bond angles are less than 90 and less than 120 degrees. Again, the less than coming from the repulsion, additional repulsion from the lone pair. T-shape. Again, we were running out of good names at this point, apparently. T-shape. Trigonal bipyramidal category of shape. So it still has 5 electron domains. Looks like this. Hopefully you can kind of see where the T is coming from. If it's like the T is on its side. If you flip it, if you turn it 90 degrees to the left, then you get your T out of this just from where the bonds are. We have 3 bonds and 2 lone pairs, right? And that is our, that's where the 5 electron domains total is coming from. Bond angle in this case is less than 90 degrees because both of the lone pairs are in the equatorial position. Which means that we get some repulsion causing, we no longer have that 120-degree bond angle because we no longer have any bonds that are 120 degrees away from one another. All the bonds are now less than 90 degrees away from one another. General formula, AX3E2. And then, again, substitute out one of the bonds for a lone pair. So we still have 5 electron domains, but now we have 2 bonds and 3 lone pairs. And we call this linear. Now this is a different linear than we saw before. This is a linear that has 5 electron domains instead of 2. Now all the lone pairs are in the equatorial position and the bonds are in the axial position. So if the bonds are in the axial position, they are 180 degrees away from one another. And it's not less than 180 degrees, basically, because now all 3 of the lone pairs are sort of providing equal symmetrical repulsion for the 2 bonds. General formula, AX2E3. All right, and our final category of shape is called the octahedral category, and this has 6 electron domains. And I know that you're probably thinking, octa means 8, so why does it mean 6 electron domains? And I'm going to let you think about that for a little while, or maybe we have already discussed it in class, but there is an 8 in the shape, it's just not in the number of bonds. So this is the octahedral molecular geometry within the octahedral category of shapes. The central atom is bonded to 6 atoms, so we have 6 bonds and 0 lone pairs. The central atom bonded to 6 atoms, again we see the wedges and the dashes indicating that the bonds are coming towards us or coming away from us, and all of the bond angles in this are 90 degrees. You can see this sort of better in class when we make some of these sort of 3D models. General formula, AX6. Then, instead of having all 6 of the electron domains being bonds, we can have 5 of them be bonds and 1 of them be a lone pair. It doesn't particularly matter where you put the lone pair. You can put it at any position, because everything is still 90 degrees away from one another, we don't have a benefit for putting it axial versus equatorial. That's kind of only very specific to the trigonal bipyramidal category of shape. Now everything is 90 degrees, so it doesn't matter where you put the lone pair, it's going to be 90 degrees away from something. So it's the square pyramidal category. We have 5 bonds and 1 lone pair. All right, general formula AX5E1, bond angle slightly less than 90 degrees due to that repulsion from the lone pair. And then the last molecular geometry that we are going through, there are a few more, but I think this is more than enough for us, is the square planar molecular geometry. This is still falling under the octahedral category of shapes, so it still has 6 electron domains. All right, octahedral, square pyramidal, and square planar, they all have 6 electron domains. But in this case, the central atom is bonded to 4 atoms and 2 lone pairs. So we have 4 bonds and 2 lone pairs. Now, in this one, it is actually very important that we do not put the lone pairs immediately next to one another. We can put the lone pairs 180 degrees away from each other. That way they're as far apart from one another as they can possibly be. And by putting them 180 degrees away from one another, that actually equals out the repulsion that the bonds will feel from the 2 lone pairs, so our bond angle goes back to being just 90 degrees. And this is called square planar sort of for a reason. If you take away the lone pairs from the shape, you see that this is kind of very much a flat square. So, you know, square planar, that's what the name is indicating. And we'll have a chance to look at what these shapes look like in 3D in class. So the general formula, AX4E2, 4 bonds, 2 lone pairs, 90 degree bond angle. The lone pairs are axial to one another. And we have 6 electron domains total. So those are the molecular geometries that we need to know. We do need to know them. So, memorize, learn them, know them. I strongly recommend that you learn these molecular geometries by looking at it in terms of how many bonds, how many lone pairs. You know, that you learn that, okay, 4 bonds, 0 lone pairs, that's tetrahedral. 3 bonds, 1 lone pair, that's trigonal pyramidal. 2 bonds, 2 lone pairs, that's bent, and go about it that way. Approach it in that regard, and then try to pick up the drawing as well.